So, all right, so the students are going to go through the same emotions that you're going through, like, I can't believe this happened, and da-da-da. Is it this, is it that? And you want to encourage that. You want to encourage them to be curious. You want to encourage them to think critically as to what works and what doesn't work. This is also a useful skill for debugging. You need to be able to debug and figure out what's wrong. All right, so some of the things that people pointed out. So what was it?
One of us, I have like, you didn't say how many, it says a AAA battery.
A AA battery.
Double A, she has two of them.
Yeah, so some groups have 2 AAs. Some groups have 1 AA. There's one other difference between the different groups. So 2 AA versus 1 AA. And I will say that every group's LED works. And some of them are blue. Blue. And I intentionally picked,
What color mine is, because it won't come on at all.
yours is red. Yeah. So the reason that they're all clear, I don't want to tip the hand that they're different LEDs, but there's some that are red, there's some that are blue. So now let's summarize this experiment so that we can understand this hidden variable. Okay.
Not a culturally,
Not culturally responsive.
culturally responsive teacher.
You got to fail sometimes. So getting used to the idea that not everything's going to work the first time and be able to figure out what to fix is an important skill. So there's a second experiment that can be done, but you've actually already done it. So there are 2 other lurking variables, whether it's 1 AA or 2 AAs, and whether you have a red LED or a blue LED. So based on the results so far, how many people had 2 AA and red? Did it work? Okay, so 2 AA red works. 2 AA blue, that works. 2 AA blue? It's supposed to work. All right, so Stephanie's doing it, let's see. Yeah, so 2 AAs and blue is supposed to work. Anyone have 1 AA and red? Okay, that was supposed to work. Now with 1 AA and red, you have to look at it very, very carefully. So do the
Dim flicker of light.
look at it end on. Yeah, if you look at the red LED end on, you can see a tiny bit of lighting. So this one does work. But the groups experiment. The first, we're going to have a mnemonic. So the red must be connected to the longer lead of the LED. The LED is our pal. So positive connects to the anode. The anode is the longer leg of the LED. So LED is our pal. Positive goes to the anode, goes to the longer leg. In order for this to light up, the resistor and the LED have to be in parallel. The resistor serves to block current flow. So because they're in parallel, the current goes around the resistor mostly and just goes through the LED and lights it up. When you put it in series, the current tries to go through the resistor. It's too much of a voltage drop across the resistor to light up the LED. So the resistor I gave is a very large resistance. It's like a mega ohm. I forgot exactly. Is it 1 or 10? Something like that. The LED actually may still be lighting up, but it's so dim that you can't perceive it. But if you measured it, you can probably detect some light. So even in series, it probably still is on. Now, in practice, and this is an important point, so this activity, it's to teach design of experiment. It doesn't teach good circuit practices. When you work with LEDs, you want to always have a resistor in series with the LED. And the reason is the LED is a current-controlled device, meaning that if I try to apply a voltage, like I apply 5 volts across an LED, I'm going to burn that out because the current that flows to the LED will be really high. I need a resistor to limit the amount of current that goes through it. So in practice, you want to have a resistor in series, but you want to have a small resistance. You want to have something like 200 ohms so that you safely limit the current to about 10 or 20 milliamps. So in practice, you want it in series. In this example, it has to be in parallel because the resistance is so large. Okay, the red LED will light up with either 1 or 2 AAs, but the blue LED needs 2 AAs. And the reason is that the energy of the photon associated with red light corresponds to 1.9 electron volts. And so a 1.5 battery, well, it's less than 1.9, it can still turn it on. So there's enough energy that it can just barely turn it on. If I got up to 2 volts, it'll suddenly be very bright. The blue LED, however, the energy for a blue photon is 2.9 eV. It's so far away from 1.5 that there's no hope of it turning on. The red will turn on even though the voltage is slightly less than the actual energy. And the reason is that there's thermal energy, and that thermal energy is enough that there's a few carriers in the conduction band that can recombine and produce the red light. And the other conclusion of this is that if you do small experiments in series, so you do some things, see what happens, and then do some more experiments, it can save you a lot of time. So rather than trying to study all 4 factors at once, we'd have to do 2 to the 4 or 16 experiments. We did 4 experiments, and then we repeated, and actually we reused the results from those 4 experiments. So we can actually do the experiments and figure things out in fewer trials than if we put everything together, because we're not wasting time doing experiments that won't work. So these are the key conclusions for this. How many of each part do you get? So I believe for this activity, you get 10 of the battery clips. You have enough batteries, so you get like 5 of the AA1 and 5 of the AA2. You actually have more than that because some of the stuff gets distributed to the students, but you have enough to probably run, if you're working in groups, with a group size of about 20.
That means you got 10 double.
I think it's something, I have to look at it again. I think it's something like 5 of the 2 and 5 of the 1, okay. So that would be 10 groups. Okay. And the groups can be 2 people or it could be 3 people, so 20 to 30 people. It's possible to also borrow parts from other activities.
That's how you know it's mine.
Doesn't work.